like to introduce the idea of an infinite series, which is just another series is just another word for sum. So the idea of adding infinitely many things together and seeing if there's a way to make sense of that. So let's just write down a few examples just to get a sense of what we're thinking about here. So I could do something kind of silly, like I could start with 1 and just add a half, and then I could add a third, and then a quarter, and then a fifth, and then a sixth, and a seventh, and so on. Keep going forever. And then the idea is this dot, dot, dot. I'm going to write dot, dot, dot right there. And that means keep going forever. And is there any way to possibly make sense of this? It's not really clear to me that it should be sort of like the way we felt about improper integrals. When we integrated from 1 to infinity, it's not clear at all that there should be a way to get any sort of sensible number out of that. And maybe this example, who knows, is there a way to make a sensible number out of this? Let me do a sort of sillier example. What if I just did 1 plus 1 plus 1 plus 1 plus 1, and I did that forever? Well, you probably could guess that this is just going to grow. I get 1 plus 1, I get 2, plus 1, I get 3, plus 1, I get 4, plus 1, I get 5, plus 1, I get 6, and that this gets bigger and bigger. This gets bigger and bigger as you add more numbers, grows without bound, right? If you just keep going forever, it's going to keep growing and growing and growing. And the way we're going to say, just like we do with improper integrals, we're going to say this diverges. Okay. And then, but let me give you another example that's kind of interesting. What if I start with a half plus a quarter plus an eighth plus a 16th plus a 32nd plus a 64th, and so on. So the idea here is that we're doubling the denominator, right, each time. So I can think of that as doubling the denominator, or I could think of it as multiplying the whole thing by a half each time, right? To go from one term to the next, I'm multiplying by a half. But if you start adding these up, so this is an important example, because I want to convince you that this actually does make sense, that this actually does, you can add forever, and you actually sort of can think of this as converging towards a finite value. So let's see if we can think about how we might believe this. So what does it mean to take an infinite sum? Well, okay, so the idea, I kind of already said it already, you sort of just start adding, and you see what happens, right? So let's just start, like, if we take a half, that's just a half, add the first term to itself. If we take a half plus a quarter, that's 3/4. Let's just keep going. If we do a half plus a quarter plus an eighth, that's 3/4 plus an eighth. And if you work it out, I think you can convince yourself that's actually 7/8, because 3/4 is 6/8. And we've added another eighth. If we do a half plus a quarter plus an eighth plus a 16th, well, that's the first 3 terms added up to 7/8, and we had 1/16. And you can sort of say, okay, well, this is really, I get a common denominator, this is really 14/16, right? So that's adds up to 15/16. And maybe you're starting to notice a pattern in the results here. Half, 3/4, 7/8, 15/16. Let's do another one just to check. A half plus a quarter plus an eighth plus a 16th plus a 32nd. Again, that the first four terms add up to 15 over 16. And if we had 1 over 32, again, if you double the first fraction, the numerator and denominator, you get 30 over 16. I'm sorry, 30 over 32 plus 1 over 32 is 31 over 32. And do you see a pattern? It looks like it's all, the numerator is always one less than the denominator, right? And the denominator is always a power of 2. So we can try to write this down as a pattern. In fact, actually, so like I want to actually give these, you learned about sequences already. This is called, there's a name for this. It's called, if I think about these numbers making a list, right? This is called the sequence of partial sums, because partial in the sense that we're stopping somewhere, right? We're not adding forever. We're actually cutting off the list somewhere, cut it off. If I go back up to the top of the screen here and I cut off at a half, or I can cut off at a half plus a quarter, or I can cut it off at a half plus a quarter plus an eighth, and so on. And just think about stopping. And that gives you a sequence of partial sums. So here we have, the sequence is 1/2, 3/4, 7/8, 15 over 16, 31 over 32. There's a couple things to notice here. So you could guess for the next one, right? The next one's going to be, the bottom is going to be 64. So the top should be 63. And so on. A couple things worth noticing. Each of these is less than 1. Each of these numbers, they're all less than 1. And if the pattern persists, the pattern suggests it'll always stay less than 1. Suggests that it's always less than 1 forever. And in fact, in getting closer and closer to 1, right? So that's our first hint that this might actually converge, that it might actually come to a finite value, that if we keep going forever, we could think of this as just adding more terms, getting closer and closer to 1. If I want to think about the sequence, though, the way to really be a little more rigorous about this, because what I want to do is I want to sort of justify that this sum is converging to 1. So let's see if we can be a little more systematic about this. So the sequence of partial sums is actually called SN. Just like, we've had sequences like the Fibonacci sequence was labeled FN and so on. Sequence of partial sums. And you've already probably tried to find patterns and sequences and tried to find a formula. So a formula for the nth term of the sequence. So let's try to do something similar here. What if I make a little table here and see if we can find a pattern? So let's start counting from n equals 1. So I'm just making this little table. Let's go up to 6. We can keep going. So we said the first partial sum is 1/2. The second partial sum is 3 over 4, 7 over 8, 15 over 16, 31 over 32, 63 over 64. And you might notice that the bottom, the denominators here, are actually, that's 2 to the first, that denominator is 2 squared, the denominator is 2 cubed, and so on. And then, so the exponent actually matches the index in. It actually matches the subscript. And so on. So you can actually guess that the general formula here, the bottom is 2 to the n, and the top is just 1 less than that, 2 to the n minus 1. So that's the formula for the partial sums of this of this series. Okay, and I'm actually going to write this slightly differently. I'm going to notice that it's kind of a nice thing to think about is if you break it up, if you break the numerator up over subtraction, you actually get 1 minus 1 over 2 to the n. So I could even extend it and say that's really one of the partial sums. And now this connects back up to the idea that I wrote up here, that you sort of really convinced now if this pattern, this pattern is holding and the partial sums are always less than 1, and 1 over 2 to the n is getting smaller and smaller, so they're getting closer and closer to 1. And the way to be super, so the actual value of the infinite series, if we call this S, I'm actually going to call S the infinite series, a half plus a quarter plus an eighth plus a 16th and so on. And I guess the way I want to think about this is we want to think about it as a limit, right? When we did improper integrals, if we did the integral from 1 to infinity, we actually thought of it as the integral from 1 to n, but then take the limit of the right-hand endpoint n and let that n go to infinity. So in fact, by definition, the sum is the limit of the partial sums, because it just says take more and more terms, right? The partial sum is the add up the first n terms. So like S sub 1000 would be add up the first 1000 terms. And then if you want to keep going, you want to add the first million terms, that would be S sub 1 million. And you want to think about doing this forever. And that's really just letting n go to infinity. And so this is important. This is like really what the definition is of a infinite series. That's the limit of its partial sums. It's worth probably writing that down. An infinite series is the limit of its partial sums. The quotes just be like, that's exactly what the definition of it means to be an infinite series. And so if we actually do that here with this example, so for this example, S is the limit of its partial sums. But we have this formula for the partial sums, 1 minus 1 over 2 to the n. And what happens 1 over 2 to the n as n gets large, right? This just goes to 0. This whole expression, the bottom gets larger, so the whole expression goes to 0 as n goes to infinity. So this sum is, if we take the limit, we just get 1 minus 0 equals 1. And so in fact, it's really, we can say it's kind of seems kind of crazy, but it's if we define everything this way, we can actually make sense of this infinite sum, 1 half plus a quarter plus an eighth plus a 16th and so on. And if we do that forever, we actually get 1. And so we say this converges, this infinite series converges. Okay, so that's kind of the basic concept of an infinite series. I might just say, let me just make one notational comment. Okay, I'm on the next page here. So the notation, we've already written sums, use summation notation before. So if we have a sequence, let me just write it this way. Given a sequence A1, comma A2, comma A3. So this is with commas in between. So the word sequence is going to be just a list of numbers. And the word series is going to be put plus signs between those numbers and make a sum out of it. So given a sequence A1, so on, we can form a series. So you just have to get these. It's weird because the word series and sequence are kind of colloquially synonyms, maybe. You think of a series as like a list of things, like a TV series or something. But in math and calculus, it's very specific. Sequence means a list of numbers, series means a sum. So we can form the series A1 plus A2 plus A3 plus A4 plus so on. And so we would actually write that as, we would write the series S in summation notation. It's the sum n equals 1 to infinity of A sub n. And actually, I'm going to change the subscript just because I want to be a little less confusing. Let's change the subscript to a different letter. Let's use I. Sometimes people use I for, I equals 1, like we did in Riemann sums. Okay, and the reason I'm going to do that is because the partial sum and here I'm using n, it's just going to be A1 plus A2 plus ... up through A sub n. And that's the sum from I equals 1 to n of A sub I, right? So that's where you make it finite. Again, you should compare this to improper integrals. And then by definition, like I wrote above, S, the series itself, is the limit of its partial sums. The limit as n goes to infinity of S sub n. And so it will converge if that limit exists, and it will diverge if that limit does not exist. So just to go back to a couple examples, just to make sure we have this. So if we take the sequence, let me examples. So if we take the sequence 1, 1, 1, 1, 1, 1, 1 forever, right? That was that example way back at the beginning. So that's A sub I equals 1 for all I. Then S, the series is the sum from I equals 1 to infinity of 1. It's kind of funny because it doesn't really have the subscript in it. S sub n is the sum from I equals 1 to n of 1. And that's really just 1 plus 1 plus 1 added together n times. And so that equals n. And then S is the limit as n goes to infinity of S sub n, which is the limit as n goes to infinity of n. And that goes to infinity, so this series diverges. So that gives the more formal argument as to why this, I gave this example way back at the beginning, all the way up here, right? We gave this example before, and that was kind of an informal argument. It sort of clearly gets bigger and bigger, but this is the slightly more formal way to talk about it, that it, to say that if it's its limits of its partial sums, then clearly it diverges. Whereas the example that we just did, if we did a half, a quarter, an eighth, a 16th, and so on. In fact, here there's a formula for this, which is probably pretty clear. It's 1 over 2 to the I, right? Because when I equals 1, if you want to think of this as I equals 1 right here, I equals 2 right there, I equals 3 right there, and so on, then the formula is 1 over 2 to the I. And then we can think of S as the sum from I equals 1 to infinity of the series is sum of 1 over I equals 1 to infinity, 1 over 2 to the I. S sub n, I guess I kind of wrote that above, but let me just write it again in summation notation. the partial sum is this sum. And we found this formula that it's 1 minus 1 over 2 to the n is the formula we found. Wasn't obvious, this was from some analysis, we did some analysis and we looked at the pattern. So it's not clear that that's the formula, but that is the formula. And then what we said is S is the limit as n goes to infinity of S sub n, which is the limit as n goes to infinity, 1 minus 1 over 2 to the n, which we said is really 1 minus 0, which is 1, and this converges. Okay, so I'm just trying to put it all back into the notation. It's the same thing we did before, but all right, so those are the basics. That's the kind of the idea of what an infinite series is and a couple of simple examples. Going all the way back to the beginning, I will say this very first example I gave, you should wonder, does this converge or diverge? I will claim that it's hard to find a formula for the partial sums. You can try. It starts to look pretty messy pretty quickly when you start adding. When we had the half plus a quarter plus an eighth plus a 16th, the denominators sort of fit in, each denominator sort of fit into the next one just by doubling. So we can get a nice formula for the nth partial sum. Here, I claim it's going to be much uglier. So, you want to start thinking about, is there a way to tell whether this goes on forever, blows up to infinity, or whether, I don't know, I mean, the terms are getting smaller and smaller, by the millionth, you're only adding a millionth, so maybe it converges. So I'm going to leave that to you to think about. All right. Scroll through this again just to remind ourselves what we did. Okay, so, all right, that's it for that.